Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. It's my great pleasure tonight to introduce my colleague, Benjamin Monreal, the Agnar Pitta Associate Professor of Physics at Case Western Reserve University. Dr. Monreal received his PhD and did a postdoc at MIT and then was an assistant professor at University of California, Santa Barbara, until moving here just this year. His research concentrates on novel experimental techniques for hard problems in nuclear, particle, and astrophysics, in particular, how we measure neutrinos when they don't care to be measured. Please join me in welcoming Professor Monreal.
I'll give a talk today about neutrinos, and I'll give this talk, unlike I think Glenn's talk from a few weeks ago, from the perspective of an experimentalist. So I'm an experimentalist. I like playing with instruments. I happen to be doing experimental work in the neutrino sector mostly these days, and I want to hopefully give you a little walkthrough of why those experiments are maybe not why they're exciting, but why they're fun to do and why we're hopeful about the technology letting us do more exciting things in the future. So neutrinos, one of the reasons that they're exciting to work on today is that there's a lot of work that hasn't been done on neutrinos because they're so hard to measure. They really don't like interacting with anything. And that's why the problems are still open. The same problems that we deal with in the neutrino sector today are things that we're answering questions that we knew the answers to about electrons or muons 100 years ago. So the questions are still unanswered today because of the neutrinos don't like interacting. So to start off with, what is a neutrino? I think I need to preview that a little bit, although I don't want to talk too much theory. A neutrino is almost like an electron. So to explain that, it sounds wrong, right? To explain why I'm saying that, let me explain one thing about electrons, then I'll contrast them with neutrinos. Electrons can do things like the interaction in this picture. You can take an electron, I think I can do this. You can take an electron and shoot it at a proton, and they will interact. They love interacting. They're very happy to do something like this. If I was a theorist, I'd be talking about what happens inside this bang, but as an experimentalist, let's just say that it happens. Typical interaction here is that the neutrino keeps going, just shoots out the other side. There it goes. It keeps its charge, that's important, and the proton has to react to whatever energy the electron has given it. So the electron goes right through this thing. Well, a common thing that happens is that you can take the proton and excite it a bit, give it some energy, turn it into a delta baryon. The delta baryon, don't worry what it is, but it's unstable, it decays, and you get out at the end a proton and this other funny particle called a pion. All of this conserves charge. So if you remember the charges of some of these particles, you can figure out if I ask you what's the charge of a delta baryon, you could figure it out from this picture. Okay, there'll be a quiz afterwards. The delta baryon has to be a +1 charge in order for everything to be conserved. There is such a thing as a positive delta baryon. And then you can also learn the pion, in this case, has to be neutral. This totally happens. It happens all the time. We do experiments on it at places like Jefferson Lab in Virginia. It's a little exotic. It sounds like particle physics. Let me give you a less particle-y example of an electron interaction. Here's an electron of fairly high energy. There it is. It's going to zip through a neon atom. You all seen neon atoms before. And these guys can interact. Notice the diagram looks exactly the same. The electron is given some energy to the neon atom. Now you have an excited atom. Excited atoms are unstable and they decay. When a neon atom decays, it emits a photon. And that's what you see when you're looking at a neon light bulb or a neon display. That's a beam of electrons shooting through a neon gas. Every time they go through an atom, they have a chance of causing this interaction. And the light you see are the photons that come out. That's why we had so much success doing experiments on electrons 100 years ago. Here's another picture. This is actually a picture of undergraduate lab experiments I used to do with our students in Santa Barbara. You can take a little tiny electron accelerator, make a little tiny electron beam, shoot it through a neon gas, and you can see exactly where the electrons are going. In this case, they're going in a circle due to a magnetic field. So here's a number which is an important number. If you take an electron and shoot it through a material, it will go through about 1,000 atoms before interacting. That's the least interactive electron you can create in the world. It's what we call a minimum ionizing particle. A particle that, an electron, there's a certain energy at which they will do this. They'll go through 1,000 atoms, they'll interact with one, they'll go through another 1,000, they'll interact with one. That's pretty good because atoms are really small. So in a neon gas like this, there are lots of atoms. It goes through billions of them, and you get plenty of photons to see. So that's the contrast with neutrinos. A neutrino is almost like an electron that's lost its charge. When the electron does, if you had an electron that didn't have any charge, it wouldn't be able to do that 1 in 1,000 interaction. If you took an electron and asked it to throw away its charge in the course of its interaction, you can do something like this. Do you see what I changed? Turned the last electron into a neutrino. Here it is. That's just, if you follow the charge along, the electron has actually thrown away its negative charge and given it to something else. We'll follow that up in a second. And that leaves behind a neutrino. It has all the electron properties except it's missing the charge. And this does happen. This is a real event. An electron can do this, but instead of doing it once per 1,000 atoms, it'll do this once per billion trillion atoms. It's an extraordinarily rare thing to happen. And in fact, this particular interaction, I don't think we've ever seen this directly. We've seen the reversed version. Did that? Oh yeah, there's the charges. So there is such a thing as a neutral delta and a negative pion. So we haven't seen this, but we've seen the reverse. Where'd it go? There it is. If you shoot a neutrino in, you can have the neutrino pick up a negative charge from the mysterious bang. And what comes out is an electron. So it's the same interaction backwards. Actually, exactly the same physics governing how often this happens. So a neutrino will go through a billion trillion atoms before deciding to bump into one. When you're reading sort of popular accounts of neutrinos, you'll sometimes see the number that a neutrino would go through a light year of lead before interacting. That's the same number I'm giving you now. You can work that out. But this interaction, it's kind of amazing. We can do this in the laboratory, and we can see it. And I want to show you an example of it. This is the reason I'm picking this kind of exotic interaction where you have a neutrino and a proton and a delta baryon. I know you guys don't care what a delta baryon is, but that's one of the first things that we saw when we started shooting neutrinos at things. Even though neutrinos are very reluctant to interact, we're lucky because we can make beams with lots of neutrinos in them, and we can make targets with lots and lots of protons in them. So if I give you a really, really rare interaction, like a neutrino plus proton goes to delta, we can actually do that as long as we hit it hard enough with numbers. A huge neutrino beam. So I'm going to show you a picture of what happened in the 1970s, I think this is the late 70s, when Fermilab started shooting neutrino beams at a couple of tons of liquid hydrogen in a tank built by Argonne National Lab. So did that display? Yep. So in gray, you see just kind of the tank itself. This tank is full of liquid hydrogen. You can't see it. It's transparent. But everywhere a charged particle has passed through, it's left a little trail of bubbles. I don't want to talk about why that is. That's actually kind of fun physics itself. But in particular, you have this tank which sat there for a while, and then there are neutrinos streaming through it. There's probably 1 billion neutrinos went through the tank in the time this picture was taken. Most of them did nothing. One of them spat out a proton, a muon, and a pion. Oh, muon. So a muon's kind of like an electron, but it's a little different. Glenn probably tried to talk about that and maybe confused you, but a muon's just a little bit like an electron. So this is basically the interaction that I was talking about before. So I don't want to talk too much about the theory, but I do want to highlight one really weird thing about this picture. The things that made it possible to do this experiment, one thing was the neutrino beam. And if you want an interesting talk, invite somebody who does accelerator physics and ask them how they made these beams. But there are two bits of detector technology that made this possible. One is that somebody had to be able to build a tank and be able to put tens of tons of hydrogen into it before you do this. You could build the most glorious detector in the world out of a gram of hydrogen, and you can sit there and stare at it for a year and not see anything, and that's not a very good experiment. No matter how perfect your detector was, if it wasn't big enough to see at least one event, you didn't really do your job. So detectors have to be big. The other thing, which is maybe less obvious in this picture, there are billions of neutrinos going through this photograph, going through the detector while this is being taken, but you don't see most of them. In fact, you don't see anything. There's lots of empty space where the hydrogen's just sitting there quiet. It's very important for these detectors to be very, very quiet almost all the time. You can't have a detector that just looks like a cat coughed up a hairball on it. You have to have a detector that sits there silently until the thing you're interested in happens. So that is the short version of the technology drivers behind neutrino physics. And if you want to imagine yourself building a neutrino experiment, the two things you want to think of first are, have I built my experiment big enough, and have I built my experiment quiet enough? So as an experimentalist, this is the kind of thing I like to sit down in the morning and design a detector. Every day I do this, and most of them are terrible. But the community is really good at doing this, and we've done it many times. And here's just a couple of little photo gallery of examples. These are all from all over the world. This is the Minos experiment. This is the Nova experiment, which is running today. This is the Homestake experiment, which is a very famous one of the early, really, really interesting neutrino experiments. Diabay is still running. And then this one in the corner is the Sudbury Neutrino Observatory. So these are all interesting experiments. They're all worth a cool talk. I used to work on Sudbury, so I'm gonna kind of focus on that one and walk you through, again, the experimental design, the experimental excitement that made it possible to turn this into a neutrino experiment. So there's Sudbury. Tiny picture zoomed in. This is a gorgeous photo. Let's see if we can look at this and understand it for a minute. I'll talk about a whole lot of the details of this, kind of walking through. But what you're looking at is a giant sphere of what is that? It's a giant sphere of stuff. And the thing I want to emphasize, so first, a couple of things. We're underground. You can see rock overhead. There's this huge thing just kind of squeezed into a tiny cavern. This is one of the best photos taken of the experiment. It's one of very few good photos taken of the experiment. It's hard to take a picture of a giant thing in a tiny room. So this is about as good as it gets. Giant thing. So this is a person. Can you see? That's a person. This is a person over there. Oh, you don't see the cursor. That's a person. This is a person. So this thing is many stories tall. This is, 17 meter diameter sphere. So that's the photo. I want to lead with the photo. This is what's inside. This is the kind of artist's concept of what's inside that detector. It has, there's a giant sort of cylindrical cavity carved out of some rock. Inside of that cavity, so on top there's the thing we call the deck, which is full of electronics. You'll see a photo later. And underneath that, hanging in this giant cylinder, is this geodesic dome, which is what you see in this picture. There's this funny geodesic dome studded with instrumentation, and in the middle of that, there's a thing we call the acrylic vessel. It's a big 12-meter diameter spherical, it's like an aquarium. In fact, it's built by a company that also makes aquariums. And that is holding our target. So when I said to do a neutrino experiment, it has to be big enough and quiet enough. So here's big enough. The Sudbury Neutrino Observatory target is 1,000 tons. It's 1 kiloton of water. Now, there's an asterisk on water because it's very special water. So you add that up, and you say water is H2O. There's hydrogen in it. So that's a few times 10 to the 31 hydrogen atoms, 6 times 10 to the 31 hydrogen atoms. The particular kind of physics that Sudbury Neutrino Observatory was interested in was solar neutrino physics. So there are lots of places to get neutrinos. You can get them from accelerators. You can get them from nuclear reactors. They're always coming to us from the sun, and there's lots of interesting physics behind that. Again, maybe Glenn talked a bit about this. And they come through in enormous numbers. And in snow, we got about 1 interaction a day. It was actually, there are a couple of different ways it can interact. One of the most interesting ones, we got 1 interaction a day. So I said big enough and quiet enough. Big enough for solar neutrino physics means thousands of tons. Quiet enough means nothing. You have to turn this instrument on and have it be just, moment of zen, nothing happening. In some sense, it's kind of scarily quiet. There was one instrument I built, as a postdoc, I built an instrument that went to Sudbury, and we installed up there. We installed on the deck above the observatory. And this was a detector that we had spent months and months calibrating on the surface of the Earth. And with the surface of the Earth is not quiet, I'll talk about this. And we spent all this time calibrating this detector and checking all the different ways it could respond to particles and using those ways to adjust how much gas flowed through it and how the electronics were tuned. We took this detector, took it apart, took it underground, or took it to snow, installed it, and then turned it on, and nothing happened. And we just sat there staring at it and said, is it working? We didn't know, because it was such a quiet environment. So quiet is good for neutrino physics. Quiet's a little weird for most experimentalists. It's a really unfamiliar way to work. So let me step forward. So then I said this thing is underground. Let me explain why it's underground. The quiet criterion cannot be met on the Earth's surface. If you want to build something like this, and I'll walk you through this, if you wanted to go to the biggest room you had, this is actually not a bad size. I took a picture of a basketball court, because a 12-meter diameter sphere containing a kiloton of water is it's most of the width of a basketball court. So that is what the snow target would look like if you stuck it on a court. If you took that, and if you really did that, just built a big water sphere on top of the ground, and said, how often does this sphere detect something? How often does something happen? The answer is about 1 million times a second. You'd have about 1 megahertz of little pings of events going through your detector. That's not quiet. That's the opposite of quiet. That would be a disaster. You would not pick out one event a day on a background of just fuzz. That's not the fault of Cavs fans or something. That's just the rock underneath the stadium, which is made out of concrete and made out of rock. And all rock has some uranium and thorium in it. You can shield that out. Radioactivity makes a kind of gentle fuzz in this kind of event. If you put a couple of meters of water around it, you could block most of that and knock it down to 10,000 events a second. Those remaining 10,000 events are not radioactivity in the rock. It's not radioactivity from the fans. It's radioactivity from space. Those are actually muons coming down from the top of the atmosphere. To get rid of those muons, you have to do something dramatic, which I don't think we want to do to the Cavs. Maybe if this was the Browns, you can just, if you put about 1 mile of rock on top of that, you could block those muons and get back. That's how you get to a quiet environment, and that's why we go underground for this kind of experiment. I'll talk a bit about how we get there, but I think I should pause for questions right now.
Based on the first slide, am I supposed to believe that electrons and neutrinos are of the same mass, and also are neutrinos kind of point particles in the same way that electrons are?
Neutrinos have everything in common with electrons except the mass and the charge. That's it. If you wrote down all of our electron equations at a kind of quantum level, and you took away the mass, you took away the charge, you basically have a neutrino. And there's a particular symmetry that we use to represent that, which is a symmetry that shows up in other places in physics, and it seems to be a really clean way to describe things. If I'm wrong about that, I'm wrong in some subtle way that Glenn will tell me about later, but I think that's basically true.
In those first couple of slides where you show the pion coming off, are we to understand that it's basically created out of the kinetic energy of the interaction?
The interaction I showed is one that's characteristic of high energy neutrinos coming in with so much neutrino kinetic energy that they can hand it off to the proton and turn it into mass. Yeah.
So your source is our sun, primarily?
For the snow experiment, our source is the sun.
So at nighttime, you've got the whole Earth is more than your mile of rock, right?
So the neutrinos they almost don't care about the Earth at all. The mile of rock is to block the backgrounds. The mile of rock is to block the muons, which are not from the sun, but from distant
supernovae. So a mile is more than enough, so the extra...
A mile is not more than enough. I would love another half mile of background reduction on a lab like this.
I'm sorry, I did not understand you. Did you say that neutrinos do not have mass then?
They do have mass, but it's not the electron mass. It's some really tiny mass that we haven't measured yet.
Okay, thank you.
When a neutrino gets in the vicinity of a black hole, does it conform to the quantum theory physics? Is it drawn into the black hole, or does it bounce off, or whatever?
Yeah, when I said a neutrino is just like an electron, it really just obeys the laws of physics just like you would expect it to. As far as we know, we haven't seen it do anything really unexpected. And laws of physics for a massive particle allow you to calculate orbits around and into black holes. just like you can for electrons. Because the neutrino is so light, it's, when you calculate that orbit, it's going to look a little closer to being a photon orbit and a little less like being an electron orbit, but the principle is the same.
You said that, excuse me, you need at least a mile to get from the sun. Now at night, are you able to get the ones coming all the way through the Earth?
Yeah, so Sudbury Neutrino Observatory detects neutrinos 24 hours a day. The neutrinos stream through everything. They stream through the Earth. And as I said, the classic number is that they would go through a light year of lead and ignore it. The thing that cares about the mile of rock is all the other stuff. All the stuff you don't want gets filtered out by that rock. And so that's cleaning up everything except the neutrinos. And there's a classic, all of the classic neutrino experiments, you always find them having some sort of giant filter in front of them to say, everything that I know about will get stopped in this filter except neutrinos. So if you build a source on one side and a detector on the other side, you know the detector is only going to see neutrinos. One of the muon neutrino was discovered at Brookhaven in a Brookhaven National Lab in an accelerator experiment where they had a beam of really just junk. They had protons crashing into some beryllium or something, and all kinds of pions and nonsense came spewing out. And they knew that there were neutrinos in that mix somewhere, and they said, we want to detect just the neutrinos. So they said, let's just put a wall of stuff in front of this beam and stop everything else. And the stuff they could get cheaply, this was shortly after World War II, so there were a bunch of battleships being decommissioned, and so they got the Navy to hand them a giant pile of battleship scraps. And they piled up walls of steel behind the beam, and the first 10 feet of steel filtered out all the pions, and the next 50 feet of steel filtered out all the muons, and there was nothing left. And then after that, they put their neutrino detector, and it's got a nice clean neutrino beam. So accelerator neutrinos you can do with 100 feet of steel. Solar neutrinos, you need that full mile of rock to get rid of backgrounds very, very thoroughly.
Thank you for joining us. You have been watching Dr. Ben Monreal discussing the enormous detectors needed to measure neutrinos coming from the sun. For more information on the Origins Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Monreal will discuss why neutrino detectors are often built deep underground in mines. Now, back to the talk.
So here's the kind of general conceptual picture of this isn't what our detectors look like. That's not what they look like. So to really get that mile of rock, we don't pile stuff on top of our detector. We put our detectors underground. And there are lots of different places that's been done, and different mines in which we've done that. The Sudbury Neutrino Observatory was built in Sudbury, Ontario, in a really unusual place. It was built in a working nickel mine. And this is the part of the history I don't actually know very well. There may be other people in the audience who know it better. The concept for the experiment was sketched out in the mid-1980s, late 1980s. And they somehow got the cooperation of what was at the time Inco, it's now Vale, which is a nickel mining conglomerate, which is in the process of working on this giant nickel ore body, which you see here in yellow. So Vale wants to get into this formation and get all this yellow, very valuable nickel ore out. And we convinced them to give us one of their drifts. So at the 6,800 foot level, it's about a mile down. It's down the number 9 shaft. There was a pre-existing drift that they'd bored for mining purposes, and they said, go ahead, take that, put your lab at the end, do what you want with it. And so we went there and started excavating this new laboratory site, which became now it's called Snow Lab. At the time Snow was running, it was just called was it even called Snow Lab at the time? It wasn't. But this is a really unique facility. Other people who have done neutrino experiments have mostly done them in kind of dedicated, like we bored a hole through this mountain just for the neutrinos, or just for the underground experiments. Snow Lab is really the big one. We're going down alongside the miners. This is not the only place in North America this happens. There's a mine ran for a long time with a lot of interesting experiments in Sudan, Minnesota. It's kind of an old iron mine. That's, I think, at the end of its life as a physics site. Carlsbad, New Mexico has a big salt mine that was being constructed for nuclear waste repository, and we were given part of that mine to do physics in. The current focus of a lot of development is a Leeds, South Dakota, where the former Homestake silver and gold mine, is being converted into a lab, and there's experiments going on there. The other funny thing I have to mention in this venue is that a very famous neutrino experiment happened, experiment was called IMB, happened in the Morton salt mine up in Mentor. And that hasn't been used for physics in a long time. People talk about going back there and doing more physics experiments there. So Sudbury, Ontario is this place in the middle of the Canadian Shield. There seems to be a nickel ore body there because a meteorite crashed into it, a billion years ago. That's where the nickel came from. But that's beside the point. So it's a little bit north of here on the other side of the Great Lakes. It's very pretty, except for these giant tailings ponds, which are green with copper residue and nickel residue. And so you go to Sudbury, and I don't know, a lot of people, when they hear that there's a science lab underground, your mental picture might be like the Andromeda strain or Resident Evil 5 or something like that, where it's an underground lab and people put on a lab coat and a bunny suit and they get into a pristine white elevator that takes them underground into a LED lit lab. Sudbury is not like that. It's an active nickel mine, so you're there with the miners. On the surface, you change into a mine suit and a hard hat. You put on a radio and a pair of boots, and you go down this elevator. There's a picture in the background. There's a little yellow barrier, which leads, if you can read that sign, it says, "Caution, keep back, open shaft." So that goes another 2,000 feet down to the lowest levels of the mine. And there's a cage that goes up and down that mine. You get into the cage. There's probably 10 scientists and 15 Canadian miners with big walrus mustaches. Thick accents, my goodness. And you all go down, then you get into the underground lab. You hike a kilometer through the drift, and at the other end of that hike, you come to this mysterious blue door. This is the old version. I haven't seen, this has been renovated. I haven't seen the new one yet. On the other side of that door is a top quality, ultra clean science lab. Clean enough to do semiconductor fabrication in. It's a very, very clean place. You have to get there from having hiked through the mud in a mine suit. So you go through those doors, you're basically in a locker room. You strip off all your mine stuff, walk through one curtain of a shower stall, shower off, get all the mine dust out of your hair. You step out the other door of the shower stall, and now you're on the clean side. And there's a bunny suit sitting there waiting for you. There's a bunny suit and a hard hat and clean underwear and clean socks and clean steel-toed boots, because it's both a clean room and kind of a heavy-duty work environment. So I couldn't find many pictures of me underground. This is one picture of me installing this funny detector underground. So you're wearing a mine suit, a clean suit, and a hard hat, and you're a mile underground. It's a really weird place to work. The air pressure, since you're so far down, it's like the opposite of being on top of a mountain. The air pressure is higher underground than it is at the surface. So you have 30% again, not 30%, 20% again more oxygen than you have here. So you go down, you have lots and lots of energy, and people go down and work long shifts and get lots of work done. So in this picture, me and Brian, who is one of our MIT technicians, are installing detectors on what's called a deck, which is on top of snow, and beneath our feet is this. So again, this is a construction picture. And I'll walk you through what all the sort of parts are. You can see in the middle this big aquarium-looking acrylic sphere, a 12-meter diameter sphere. That's what will get filled with the ultra-pure water, which is our target. Around that, and you can just barely see it here, are a whole bunch of little gray dots arranged in triangles. And they're being assembled in this photo. And those are the light sensors. Those are the things that are going to detect that an interaction has happened. And all of that is kind of hanging from the deck, suspended in this cavern. And all of this is going to get filled with water to serve as our radiation shielding. I want to show you one photo. This is a photo taken with a fisheye lens looking up after all the PMTs, after all the sensors were in. So you're looking at the bottom of the acrylic sphere and those photosensors all around it. So we've gone underground, we've gotten rid of the muons. That came at great expense, it came at great complexity. This whole thing was put together out of parts small enough to fit in an elevator, all glued together by this fancy aquarium company, Reynolds Polymer. We've gotten rid of the muons by that. When we fill this with water, we get rid of the radioactivity. And now it's time to detect neutrinos. So what happens when a neutrino interacts, and I will walk you through this, a neutrino interacts, and most of those interactions will result in a high-energy electron somewhere in the water. That electron is of such high energy that from the water's perspective, light wants to move slowly in water, but this is an electron moving fast. The water thinks the electron is moving faster than light, and it kind of freaks out, and it responds by actually emitting a bit of light itself. It tends to be on the blue end of the spectrum. It's called Cherenkov radiation. And so that light goes splaying out from wherever the electron's going. The light splays forward, and it goes through that acrylic vessel. That's why we chose acrylic, because it was transparent, and it hits these little dots on the side, and those are called photomultiplier tubes. So the reason we have a neutrino industry, the reason that we're able to do these experiments at all, is that we have 80 years of R&D developing these gorgeous photosensors. It's one of the key technologies that makes this possible at all. Your lives are already full of very tiny versions of this. All these little tiny things at the bottom are photomultiplier tubes. They're in your medical imaging devices. They used to be in cameras. They used to be in like the light meters you'd hold up if you're taking a picture with an old film camera. The little tiny ones are all over the world. The big ones, like this 20-inch thing at the top, those are built by and for particle physicists only. The 9-inch one on the side is the one that that Sudbury was using. We had 9,600 of those guys, costing probably $4,000 each. They're expensive. And these are single photon sensors. So one particle of light, the absolute minimum light beam, can hit the surface of one of these things and give you a detectable electronic signal on the other end. They actually work just like a television in reverse. If the older members of the audience may remember when televisions looked like this, they were a big box with a vacuum tube in it, and there was an electron beam that would come out of the back of the television, shoot through the front, and hit a screen. And when the electron hit the screen, it would get absorbed, and that would emit light. It was called a phosphor. If you do that backwards and with slightly different optimizations, you can have light come in, hit a phosphor, and emit an electron. And so it's a TV running backwards. So it detects every time light hits the screen. So it's kind of amazing. You can take something the size of a TV and have it sit there quietly until one photon hits it, and then it goes blip and makes a little signal for you. So that's a technology we've been using for the first of these things these came from electron tubes that we had almost 100 years ago. The sort of modern looking one is probably 70, 80 years old. And the technology has gotten better and better. They got more efficient, and people are still working on this. And I look forward to the day when we can build neutrino detectors without PMTs, but with whatever follows the PMT. CERN was working for a while on this very exciting thing called an XHPD. I think that effort faded away. I'm not sure. Chicago's working on this amazing thing that behaves like a PMT. It detects single photons. But instead of being a big TV shape, it's flat. It's the flat screen TV of photon detection. And it has it's beautiful other properties. People have built these out of quartz at UCLA. People have built silicon things that are almost as good as PMTs now. And that's what you need to instrument this detector. That's what you need to coat this whole sphere and see what happens. So here's a picture of a event in snow. And so that's the snow sphere just as a picture. I'm going to overlay on that a little cartoon with a green spot everywhere that a photodetector thought it saw a photon. So you see the whole sphere. Some of the photodetectors are black. They didn't see anything. Some of them are bright yellow or bright green. That means they saw lots of light. Some of them are fading to orange. That means they saw a whole lot of photons at once. Do you remember I said that about once an hour, even though we're a mile underground, maybe once an hour we still get one of those muons coming through, one of those background events we didn't want. This is one of them. It's a high energy muon that was of such high energy it penetrated that whole mile of rock and got to snow. And this is what it looks like. It lights up the whole thing. It's like a Christmas tree. It lights it up so bright that you have to sort of back off and ignore the next 100 milliseconds of data, which is waiting for everything to calm down, because this is such an exciting event. So those are high energy, what we call muons, high background cosmic ray muons. That's in stark contrast to, here's another one. This is what our signal looks like. when a neutrino interacts with our water, makes a little tiny electron track, emits just a little tiny bit of Cherenkov radiation. And you can maybe see those green spots. Those are all single photons. One photon, one PMT. What is that? Probably 50 or 60 of them. They're in a ring because that's a property of Cherenkov radiation. It radiates out in a ring from, in a cone from wherever it started. 50 or 60 of them tells you what, sort of what counting those photons tells you about what the energy of the electron was to start with. Measuring the size of the cone actually tells you a little bit about where that interaction happened. If it happened on the far side of the sphere from you, the cone comes out and it hits you and the photons are all over the place. If it happened right next to you, the cone is small. So this lets you spatially localize. We use the intensity information, we use the timing information. Everything these PMTs tell us went into our code somewhere to try to deduce as much as we could about the event. And yeah, this would not, it's many things about snow, you look at them and you say, well, this experiment actually ran from 1999 to 2006. If you try to imagine it running in 1970 or 1975, you couldn't have done it. It would not have existed. We didn't have the techniques yet. We didn't have these PMTs that were this good. We didn't have the computers that could analyze data like this at the speed we needed to. So a lot of technology goes into giving us pictures like this. Yeah, that's the thing that got me into particle physics and got me into experimental particle astrophysics, was the really cool stuff we can do with the latest sensors, the latest detectors, the latest chemistry. Let me pause there and take the second round of questions before I move on and show you some interactions.
How fast is the event?
The neutrino hits an electron. The electron is moving at, the electron only goes like a centimeter or so in the water. So the electron is only sitting there radiating at you.
No, I'm talking about how fast do you capture the data?
The electron's only sitting there radiating at you for less than a nanosecond. The photons arrive over the course of, or the little signals arrive spread out over probably a couple of microseconds with a bunch of cable delays. So we have a lot of electronics that take a sort of a microsecond's worth of data and bring it together and call that an event.
And that's digitally captured?
Yeah, the PMTs are getting from, let's see, do I have a picture of this? Getting from the PMTs up to the deck is analog. The PMT just has a coax cable coming out the back. We digitize it as soon as it hits the deck. And then those get built into events that get saved to the disk. Different experiments differ on how digital or how analog they were, and snow was fairly conventional in that respect. Some people tried to digitize right at the PMT and just say, I just want to send a pulse that says yes or no, I got hit.
How do you know that the photon is generated by a neutron as opposed to a muon? I mean, by a neutrino as opposed to a muon? We
have a whole lot of software that compares what was seen to either simulations of, what would it look like if a muon went through. We can calculate that. We can make a model of it. And we also did there's lots of calibrations. One of the calibrations, actually, your particular question harks back to this picture. This picture is me and Brian and a student, Tom Sonley, installing a detector on top of snow that would see muons coming through specifically. So we were waiting for this detector and snow to fire together to confirm that those were real muons and to see which direction they were going. So we used information about the event. You can see in this sort of picture that, where's my picture go? I have to jump forward. The muon events look different than the neutrino events. Muon versus neutrino is actually very easy to do. The hard part I will explain in the last part of the talk when we have to distinguish neutrinos from everything else. But yeah, it's a giant data analysis problem, is what it is.
Since these neutrinos have some mass, do they ever slow down?
So the neutrinos that snow is interested in are neutrinos that have millions of volts of kinetic energy, millions of eV kinetic energy. Their mass is probably more like thousandths of an eV. Their mass is probably, so they have far, far more kinetic energy than they have mass. And so from the perspective of snow, their speed is identically the speed of light to, I can probably figure out, to 18 digits of precision. Their speed is exactly the speed of light. It's not exactly the speed of light, but it's so close that we'll never see it. So we did not have any kind of neutrino speed measurement. And in fact, nobody on Earth has yet measured a neutrino speed that showed any evidence of their mass at all. Speed measurements are very, very hard to do in this sector, and it's not the way to do it.
In that diagram there is the mean diameter of the circular green dots pretty much the same all the time, or does it vary?
No, it varies depending where the event happened in the sphere, and it also varies depending on the electron energy. An electron with very low energy can make a slightly smaller cone. An electron with higher energy makes the maximum cone. That's not a very sensitive way to measure the energy. And then, yeah, depending what the geometry of the cone is with respect to the sphere, it can be all kinds of different shapes. It's not always round.
Were those aluminum wide flange or I-beams or angle iron?
That was, I believe, all steel tube construction that did that.
Oh, steel with the coating on it then?
Yeah, that was all built at Lawrence Berkeley Lab. That was all built before I arrived, so I was not involved with that geodesic thing at all. Steel, I'm pretty sure of.
All the green dots up there are the neutrinos.
Those are the photons emitted by the electron that the neutrino turned into.
Okay, now what are the blue dots?
So let's see, if there's a blue dot, that's probably, I see, yeah, that must be a PMT that gave a slightly lower response, like maybe a PMT that pulsed but not in a way that triggered properly. They should all be, they should all be sort of 0 or 1. You either saw an event or you didn't, but there's an analog step in there that could maybe make it a little fuzzy. I'm not sure what the color scale is supposed to do. In an event of this size, there should not be any PMTs that got 2 photons at the same time. That's very unlikely. So I think those are probably sort of weak pulses from.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Ben Monreal. Dr. Monreal recently joined Case Western Reserve University from the University of California, Santa Barbara. In the second part of our talk, we learned about some of the technology behind the enormous neutrino detectors. In our final segment, Dr. Monreal will talk about the Sudbury Neutrino Observatory in Sudbury, Ontario, Canada. Now, back to our talk.
I will show a couple of these neutrino interactions. So inside SNO, we saw, I introduced this by saying that a neutrino turns to an electron. There are a couple of really interesting ways that happened, and they are sort of key to understanding this technology. This is what SNO, one of the 2 things that SNO was most excited about seeing. You have a neutrino come in, and most of the time I've talked about, what happens when a neutrino hits a proton. The more interesting thing happens when a neutrino hits a neutron. So you can have a neutrino crash into a neutron. They do one of these charge exchange interactions, this charged weak current, and out comes an electron. So the neutron sort of donates some charge to the electron, and that turns it into a proton. So this is a characteristic sort of neutrino interaction that you can get from when you're using the sun as your source. And you can look at all the charges and confirm, yeah, this looks like it ought to really work. The funny thing, the thing that looks like it doesn't work is, I say, how do I get a target made out of neutrons? I didn't put 10 to the 31 neutrons into a mine. I put water into a mine. Isn't water made of protons? So we had to do something very special, which is we got a supply of heavy water. So if you know, heavy water is most often associated with the nuclear industry. So you hear about it from the Manhattan Project and the Alsos mission. It's all part of the story of early nuclear physics. And that heavy water has, instead of hydrogen, has heavy hydrogen, which is a proton with a neutron stuck to it. It's actually stuck very gently. So SNO got a kiloton of heavy water, and which is, again, one of these really bizarre things. Why was there a kiloton of heavy water in the world? It's associated with the Canadian nuclear industry. The Canadians have a weird reactor design that uses heavy water as their coolant. And it's a funny thing. If you had tried to build SNO, if you tried to ask Canada for a kiloton of heavy water in 1960, they would have said, no, we need that for our reactors. If you ask Canada for a kiloton of heavy water 20 years from now, they're going to say, no, we don't have any heavy water. We don't use that kind of reactor anymore. So snow happened in this one little window when they had stockpiled lots and lots of heavy water, but the reactors hadn't come online yet. So they had it sort of on loan, and they loaned it to our experiment. So it was one of the largest supplies of heavy water ever to leave one of these atomic sites. Although we later found out that when we finished using it, we gave it all back. They put it in 55-gallon drums on a disused hockey rink, which is one of the most Canadian parts of the whole story, was the fact that they stored their precious $300 million worth of water was stored in the hockey rink. So when that deuterium is in there, the neutron is the one that really interacts with the neutrino. The other proton just kind of hangs around, and it escapes without doing anything. So I said the thing snow really detects, the thing that emits the light is always the energetic electron. And you can all see there's one energetic electron in there. We can see that. Here's the other totally crazy thing that snow was able to do that nobody else was. Neutrinos don't have to give up their charge when they interact. They can undergo something called a neutral weak current. They can bump into stuff just as though they were electrons, but with this very rare probability attached. And here's an example of that. A neutrino could bump into a whole deuterium nucleus and have no effect on it, no charge exchange, except it just breaks it up. So oh, you were a neutron and a proton stuck together. Now you're a neutron and a proton bumped apart. It costs 2 MeV of energy to do that. You have to put energy in to knock them apart. Neutrino loses a bit of energy. So this one, you would think, this looks like nothing happened. It looks like the detector is going to be totally blind to this because there's no electron. So we had to do some choreography to get this to put out electrons. One of the choreographies we did was, at times, snow was full of a little excess of sodium. We actually dissolved some basically table salt in there. When there was sodium present, the neutron captured on the sodium. That made an excited sodium isotope which wanted to emit a gamma ray. Once you had gamma rays, the detector is also made of electrons. The gamma rays and the electrons interact, and there comes your energetic electron. So it's this 3-step process to get a neutral weak interaction to turn into an energetic electron. Really bizarre process, never seen in low energy neutrinos except by snow, because it required this weird choreography and it required deuterium. So this choreography was proposed by Herb Chen, who was a UC Irvine professor of physics, nuclear physics, who passed away in 1987, which was after snow had sort of gotten started, but before he got to see the results. The sort of co-leader of snow in its early days, who remained spokesman for most of that time, was Art McDonald, who was awarded the 2015, co-awarded the 2015 Nobel Prize for precisely this work. And everybody was really thrilled with that. A lot of people, it is something we sort of saw coming. Everybody said, well, Art should probably get the Nobel at some point. In 2015, when the announcement came out, I was at a conference with a bunch of other neutrino physicists, about 10% of whom had been snow veterans. And so we were all, as people do at conferences, you're ignoring the speaker and everybody's checking email on their laptops. And so all of the snow people got this email at the same time saying Art got the Nobel, and there was a little flutter through the room. And everybody turned around, and then eventually the news filtered out to the non-snow people. So that was a really cool thing. And that was done, I think that was awarded specifically for this wacky interaction, for seeing the neutral current for the first time. The other things that neutrinos can do is really weird, and it doesn't depend on the heavy water. It's just a neutrino can crash into an electron, exchange charge with it or not, and kick the electron. So you can get a high energy electron from this, just what we call elastic scattering. For that, you don't need heavy water. And so another experiment called Super Kamiokande got a much better view of this just by virtue of being bigger. Super Kamiokande had 50 kilotons of water in comparison to SNOW's 1. Super Kamiokande was actually able to see this interaction so well they were able to take a picture of the sun from underground. The red and yellow and white dot is what the sun looks like if you measure it by seeing what direction the elastic scattering electrons come from. So that's a photograph of the sun taken 24 hours a day from deep under, in this case, Japan. And so Professor Kajita shared the Nobel Prize with Art for his work on Super K and this similar thing. Okay, so the other technology I want to talk about, the other technical issue with these experiments is the fact that high energy electrons are not that hard to come by. SNO and Super K, these experiments get our high energy electrons from neutrino interactions, but what happens if there's a little bit of, say, radioactive thallium, thallium-208, dissolved in your water, which is very happy, thallium's very happy to do that. Thallium-208 decays. It's a radioactive nucleus. It's part of the, which one is it? It's a thorium product. It decays to lead-208, emits a gamma ray. Gamma ray hits an electron. Your detector's full of electrons. Now you've got a high-energy electron. It's going to make a signal just like the one you're interested in. It doesn't have to be gamma rays. Something like bismuth-214 is a beta decay nucleus. It's in the uranium chain, unless I have them backwards. It just decays and emits a high-energy electron. So if you have a detector which has all this other stuff in it, you're going to get little rings showing up from high-energy electrons, and you're not going to know, was that a thallium ring, was that a bismuth ring, or was that one of my neutrinos? The only way to be sure, well, there's some data analysis you can do to try to separate them statistically, but the first thing you do is just try to clean everything up. Say, I'm going to fill this detector with the cleanest water on Earth, and at the time snow was running, it was, at large volumes, it was the cleanest water anywhere in science. This thing had been scrubbed, and it all had to be scrubbed underground. So about a third of the footprint of the underground lab, there was one big cavern that contained snow and all of its electronics. There was one big cavern that had a lunchroom and a coffee pot and the showers and things. And there was one big cavern that was just full of piping, full of distillation columns and ion exchange columns and everything we had, every tool in the arsenal for getting metals, getting dissolved materials out of water. And so we got that water down to ultra low radioactivity. The uranium thorium in the water we think was probably something like 1 part in 10 to the 14. So 0.01 parts per trillion, 10 parts per quadrillion. Extraordinarily clean water. And with that presence of a little radioactive background in the water, after cleaning it all up, when we saw little rings like this, we saw these little events. About 10% of those events were not neutrinos. About 10% of them were our remaining background, the stuff we couldn't get rid of, even after all our best efforts. Some of the background reduction efforts were really bizarre. On the acrylic vessel, there was one little spot which remained hot. After we built this thing in a clean room, everything was scrubbed. There was one little spot which ended up being called the Berkeley blob. And as far as we can tell, somewhere in this one little piece of acrylic, there was an extra 9 micrograms of thorium. Nobody knows where it came from. Nobody knows how it got there. Nobody knows what form it was in. It's approximately what would happen if you'd gone through the whole mining process and come in for if you came into your shift assembling acrylic and you hadn't washed your hair in the shower, and you had some mine dust in your hair, and you're sitting there assembling the acrylic vessel, and you ran your fingers through your hair and touched the acrylic vessel. That would give you about 9 micrograms of thorium. So maybe that happened once. We had a little hot spot, and that contributed about 10 events over the history of the experiment, about 10 extra little rings that were not neutrinos. So everybody in the neutrino business has to deal with stuff like this. The Borexino experiment in Italy was the one that sort of knocked it out of the park and showed everybody else how to do it. So snow got to 1 part in 10 to the 14 atoms. Borexino got to 1 part in 10 to the 16. They got their radioactivity so low, they couldn't measure it anymore. They were trying to figure out what radioactivity background they had, and they couldn't see it. They could not determine what was happening in there. They just knew it was really low. They actually built an entire copy of their detector devoted entirely to radioassays. The rest of the community has put an enormous amount of effort into radioassays. Every material that goes into an experiment has to sort of pass by a germanium detector first and make sure we count it. Is this manufacturer making cleaner steel than this manufacturer? Has this welding rod ever been near a welding rod that was using thorium? Everything gets checked. And nowadays, it's all getting cataloged online, which just makes everything so much easier. You don't have to measure everything yourself. You just have to figure out if somebody else has measured it. But we're getting better and better at this. And so every new generation of experiments is getting a lower background than the one before. The thing I would really love to do in the distant future would be to build experiments out of materials that don't have radioactive backgrounds. The best neutrino experiment you can imagine would be one made entirely out of neon. Especially liquid neon, because there's no bismuth that dissolves in liquid neon. There's no thallium that dissolves in liquid neon. Neon has no radioactive isotopes. So I have a daydream that someday I'll build a 10 kiloton neon experiment with zero background. They don't have to worry about all this stuff. So let's see, in my last couple of minutes, let me give you just a quick view. So neutrino physics, I've talked mostly about it historically. It's mostly SNO happened in the past. It got its results, it published them. It actually has a paper out just now. It's one of its last papers is just coming out. It won its Nobel Prize, but neutrinos we're not stopping. So three big experiments and a whole lot of small experiments are coming online in the next decade. And all of them have at least one aspect where you're saying, this experiment was not possible until we got to the bleeding edge of one of our technologies. Juno is a big reactor experiment in China that needs just the absolute best phototubes on Earth all over the place. Their phototubes need to be so good that they're probably going to put in, tile their system with 9-inch phototubes and then fill the little gaps between the 9-inch phototubes with 3-inch phototubes just to make sure they get every photon. Hyper Kamiokande is in the design phase. It's going to be 500 kilotons of water. I don't think it's ever going to happen unless they get phototubes that are a little cheaper than they have now. So there are a lot of people working on the manufacturing process. And they need the world's clearest water. They need water with 100 meters, or of order 100 meters of clear, zero absorption water. Dune is a big liquid argon experiment. That's the big one going in South Dakota. They need the world's purest argon. They're not there yet. There's an entire research program devoted to building test detectors just to practice purifying your argon. So the PMT frontier is going forward. The radio purity frontier is going forward. One frontier that hasn't moved very far is the mining frontier. We're still mining out these caverns today, more or less the same way we mined them 50 years ago. I have one of my wacky pet projects is the hope of advancing the mining frontier a little bit by putting a high pressure inflatable detector into a salt dome. What is bleeding edge about this? The bleeding edge thing here is that it's a high pressure inflatable detector in a salt dome. That's never been done before. It's something I'm excited about, and it's actually one of the things that in part brought me to CASE, because you guys have salt. Like just straight down from here, a kilometer or so, there's a big salt bed that someday I will do this to, if they let me. Go into a big salt dome, drill a pipe into it. In that pipe, pump a bunch of fresh water. Fresh water hits salt and it dissolves it. So you can get the salt water dissolves out. I'm not making this up. This is standard gas industry technology. And so if you pump enough fresh water down one of these pipes, it turns into salt water, dissolves salt, the salt comes up, and you're left with a big bladder, a big bubble of salt water sitting in the middle of your salt dome. This is incredibly stable. You can just leave this thing open, forget about it, and it'll sit there for 100 years. It'll slowly, slowly shrink. So this may be the thing that I want to really get out of physics, which is a new route underground. It doesn't involve all the same constraints about chopping up your detector into little pieces and bringing it down a mine. It doesn't involve the bunny suits. It doesn't involve the hard hats. It just involves somebody sitting at the surface figuring out how to lower stuff down a pipe on a wire. Nobody's done it before, but maybe someday we'll have one of these kiloton scale detectors. Maybe my 10 tons of neon will be down there. And I think there may be a future for advancing the mining frontier in parallel with all the other things we're doing to make instrumentation better to keep doing neutrino experiments. That's the end of my talk. Thank you very much for listening. I'd be happy to take more questions.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.